Good day, class. My name is Dave Stone. I'll be your instructor for the term. This is MSTM 4008, an introduction to oil and gas. This is topic 1, origins and overview of oil and gas. The learning objectives for this week are to describe how hydrocarbons are generated within source rock, list and explain various types of hydrocarbon traps, explain the major parameters to classify crude oil, discuss classification schemes and benchmarking crude oils, explain the difference between conventional and non-conventional oil, and explain the difference between reserves and resources and how they are categorized. Key terms for this section are kerogen, source rock, reservoir rock, migration, hydrocarbon traps, sweet and sour, geographic location, benchmarking, shale oil, proven, probable, and possible reserves, barrels of oil equivalent, conventional and non-conventional crude oil. Now folks, that'll be the end of me reading to you for this term. Trust me, you'll thank me for that later on. Einstein said that if you can't explain a topic simply, you do not understand it well enough. I like the concept of that, and therefore I try to teach in small 2 or 3 minute stories, where I try to shrink down a complex story well enough so that my 13-year-old daughter understands. I hope you enjoy that style and the course itself, and let's get started. Thank you very much. So here we go. For hydrocarbons to accumulate and be converted into source rock, you need a couple of conditions. I always love the story where dinosaurs die, they get buried, and over time they turn into oil and gas. That's even a little simplistic for me, so we're going to try to expand on that a little bit. First, you need a sedimentary basin, and basically it's a big hole or trench or in the ground, and I'm going to use it in the bottom of the ocean as my example. So you have a big trench or a hole in the bottom of the ocean, and as things die in the ocean, plankton, your dinosaurs, prehistoric, anything organic, it falls towards this basin or hole. Due to ocean currents, its location, it's just very strategic, and everything is just accumulating here over time. So as water rushes off the ground into the ocean, all this organic matter is being carried in as well. As it's going in, it's being carried in, and also sand and silt are covering it. So as the organic matter is coming in, it's being covered by sediment as well. And over time, and we're talking geological time here now, so thousands, hundreds of thousands, millions of years, this is all being covered and covered and covered to a point where it's totally covered in, and now temperature and pressure are pushing down on it and is actually converting it into what we know as source rock. Good evening. This next slide is to explain sedimentary basin types, and they're pretty simple: rift type, trench type. They're the geological names. But my favorite is to explain is a pull apart, only because of my explanation. I saw this on YouTube. And my favorite food is Snickers bar. So if you can imagine that this side here is a mountain and this side over here is a mountain, and they're on 2 different tectonic plates, and as they pull apart, okay, if I can do this properly here now, it creates a small hole or gap in the center where all the toffee is. So as you can imagine, as rain and erosion starts, all the water runs down here and runs down from this side into your basin, which is the toffee section. Everything collects there, and we'll talk about a little bit later about clastic rock, but all the rocks that come down are rather large in size, pebbly sized, and they collect here, and the organic matter is buried in the sedimentary basin, and over geological time, like I said, it all collects and collects. And that's my explanation for pull apart type sedimentary basins. That's another reason why oceans are a great example of a sedimentary basin. Like I said, there's a trench or a hole in the indentation in the bottom of the ocean where everything collects. So it all collects all the dead material, organic material. But it's not just that as well. It's also the atmosphere. It's an oxygen deficient atmosphere or an anaerobic atmosphere, which prevents decay of the material as well. So if you can imagine something dies on land, just being open to the elements, the sun, the wind, it disappears, it disintegrates. But where it happens in the ocean, it all falls into the bottom of the basin, collects, and it doesn't decompose fully. And therefore, then sediment comes in on top of it, collects, and then it stays like that. Eventually, over time, it all gets compressed and turned into source rock. Also, you need a huge amount of organic material. And usually you need a life-changing event like that, where either a volcano erupts, or an asteroid hits the planet, or an ice age, where an extinction level event where everything on the planet, but a lot of things on the planet, all the organic material dies and falls into this basin, and that's why periods like the Middle Cretaceous, Late Jurassic, Devonian, Silurian, those times and geological times, there's an event there that has an extinction level event where a lot of the organic material on the planet dies and collects. So when people are drilling for oil in the ground, they're looking for stones from the Middle Cretaceous, Jurassic, and Late Devonian periods. So now you have all this organic material in a basin, covered up, and all ready to be changed and converted into source rock. So it's like baking a cake. For the bakers among you, you need a nice oven, a nice warm oven at 350 degrees. If your oven is 500 degrees and you put your cake in to bake, it turns black on top and the center's all gooey and it's not a cake. Same thing here. If you have the wrong temperature, wrong pressure, not enough, too much, the organic material turns into other things, coal, shale, items like this. So you want to have the perfect pressure and temperature to turn your organic material to chemically change into a thing called kerogen. We'll explain kerogen now in a few minutes. And this ideal pressure and temperature is referred to the oil window. And the oil window is typically 80 to 220 degrees Celsius, or 2,500 to 9,000 meters in depth for pressure. So for the drillers amongst you, or geologists, you'll have a better understanding of the oil window and pressure gradient. So for the first 200 feet, when you're drilling into the Earth's crust, there's not a lot of fluctuation, maybe 11 degrees between 0 and 200 feet. Nothing too big or fancy there. The next 200 feet down to 400 feet, it does fluctuate quite a bit. It's not nearly as steady as you'd think that it would be, usually because of groundwater running in around the areas. But after you hit 400 feet, everything kind of steadies off. As you go deeper into the ground, it just increasingly gets hotter and hotter and hotter. As a general rule, for every 100 feet you go down, it increases 2 degrees Celsius. My 12-year-old daughter made this slide for me, if you can imagine. And what I wanted was a picture to really encapsulate and explain the oil window. I think she did a pretty good job of it. So here we have the range here in temperature and pressure, 150 degrees to 225. And if you have an organic rich sediments, chemically changed to kerogens, that will transform with proper temperature and pressure into a gas pocket. For here, for 150 to 75 degrees Celsius, same thing, you have organic rich sediments, and under that temperature and pressure, it should turn into oil. Right. I also mentioned if you're outside the range or the window, that same as baking a cake, an ideal temperature baking your cake is 350 degrees, but if you bake it at 500, it burns on top and the center is not cooked. Same thing here, if you're outside the window, it won't form oil and gas, but it'll form something different. Maybe tar sands, shale, coal, something of that nature. We've been throwing this term kerogen around for the past couple of slides now, and it's not a word you use every day in spoken language, so I'd like to explain it a bit. Kerogen is a waxy organic chemical compound. So once your organic material in your sediment rocks is squeezed and under pressure and temperature, it undergoes a chemical change and becomes a thing called kerogen. And we mentioned earlier, anywhere from 75 to 150, it squeezes and becomes oil. And from 150 to 200, the right pressure and temperature, it becomes gas. Shales rich in kerogen that have not been heated properly, like I said, they're outside the oil window. They may form shale deposits or tar sands. Kerogen itself is very much like bitumen, really. It's really thick tar. All the organic material has now chemically changed into kerogens. The kerogens have been cooked properly under pressure and temperature within the oil window, and now they are transformed into oil, which is a liquid, and or into gas, which is a vapor. And as liquids and vapors will travel upward, and this upward movement is called migration. If you have a bucket of water and throw oil in on it, the oil will eventually rise to the surface. Same idea here. As the oil travels up, it usually accumulates into a very permeable rock known as reservoir rock, and is very porous, which enables the oil to flow when it is drilled. So here's a good slide that kind of brings it all together. So here's the bottom of your basin, and everything is collecting in here, all your plankton and clay and so forth and so on. It's all collecting in the bottom, and over time and it forms this layer right here. Then sediment falls over it, so it's in an anaerobic atmosphere and doesn't decompose. As you notice, the sediment layers start building up and building up and building up. As they get higher and higher, it increases temperature. And now the organic rich mud now turns into black shale from heat and pressure and turns into kerogens. And it gets warmer again into 120 degrees Celsius. So now you're in the window for the making of oil. And as you can see, more weight on top. And now the migration starts as it squeezes out and turns into a liquid form, and it travels upward. So now our oil and gas is made, and it is starting to migrate up. It's migrating up through the sediment that covered it and made it initially. And that sediment rock is referred to as reservoir rock. And there's two main types. One is clastic and the other is carbonate. We're going to talk about clastic first. Remember a few slides back I had my Snickers bar and I pulled it apart. It said both sides of the chocolate are mountains, and as the rainwater rushes off, it brings down through the rivers all kinds of pebbles and rocks and so forth and so on. Well, that forms this type of rock right here, clastic rock. These are all the rocks and pebbles came down from the mountains. Another type of reservoir rock is carbonate, which is the chemical reaction between calcium and carbonate. And when I talked about the sedimentary basin at the bottom of the ocean, a trench or a hole that everything falls into. So it's a constant rain of the tiny shell fragments and algae and all the microorganisms that fall down, and they're buried, and this becomes limestone, right? And this is the other type. And like I said, the oil travels through here as well. It's quite permeable, and that's your other type of reservoir rock. Our next topic is hydrocarbon traps. So your source rock now has been squeezed by pressure and temperature to convert it into oil and gas. The oil and gas now is traveling through reservoir rock, a highly permeable rock that allows it to travel. It comes up here, and it is now encapsulated or trapped into a cap rock or impermeable rock, and that stops it moving laterally and upward, and it makes your reservoir of oil and gas right here. And all you got to do now is drill a hole in the ground to collect it. These next couple of slides I'm going to kind of whiz through. It's not because it's not important, it's just because really I don't have anything to elaborate or explain it. It's kind of just pure memorization. There's three main types of hydrocarbon traps which I want you to be aware of. The first is structural, next is stratigraphic, and the last is combination. There are two main types of structural traps, and the one probably going to discuss probably the most and use as our analogy is the anticline trap. The other structural type is the fault trap, where actually two tectonic plates shift and trap oil. The second type is the stratigraphic type trap, and basically it's impermeable rock on one side, impermeable rock on the other, and impermeable rock on the top, and the oil and gas gets trapped inside. And the last type is the combination trap, and as the name suggests, it is a combination of processes which form through tectonic activity, and a reservoir is made. As I mentioned earlier, the anticline trap is probably my most discussed, basically because it's a nice simple diagram to explain and understand. First you have right here, you have the cap rock, which encapsulates all the oil from the reservoir rock. And so the reservoir rock is through here. But if you look at the diagram, it looks like the rock stops here, and there's a level of water, and there's a level of oil, and there's a level of gas. That is not actually the case. It's drawn this way so you can visualize it, but yes, the reservoir rock is porous. So what happens is this reservoir rock is all the way up through here and down, as you can imagine, and the water is in the spaces between the rock. And same with the oils in the space between the rock and the gas up here. So the reservoir rock up here travels up and along, and all of these are in the spaces between it, in the pore spaces. Crude oil classification. Geographical region where it is produced is the next category, and things you'll see are items like West Texas Intermediate or Bonny Light or Arabian Light. If any of you worked on oil tankers coming out of the Persian Gulf, you may have carried a cargo called Arabian Light or Arabian Heavy, obviously originating in Saudi Arabia. Bonny Light is from Nigeria. West Texas Intermediate, I can't imagine any of you really transported it around the world yet, mostly because West Texas Intermediate has not been exported for decades. And it's only recently that the United States has lifted the embargo, and they're going to start transporting oil. So even though it is a benchmarking crude, a lot of you probably haven't transported it ever. Another benchmarking crude which I want to talk about, which is not on this list, is Brent crude, which is a basket or a collection of different types of crude oil from the North Sea. And when you see prices of oil being posted, you're usually referring to Brent crude. The next criteria for crude oil classification is density, and that is measured by API, the American Petroleum Institute's inverted scale for measuring density of crude oils. I don't want to get too tied up into the API classification. What I want you to know is the magic numbers. Anything above 30 is referred to as a light crude. Anywhere from 22 to 30 is medium, and below 22 is referred to as heavy. To give you an idea what below heavy is, asphalt is an 8. That's quite dense, as you can imagine. I've also got here crude oil. Brent is the leading benchmarking crude oil on the planet currently, and if anytime you're seeing a crude oil price posting, it's usually referring to Brent crude, and that is a nice light crude of 35.5. The third criteria for crude oil classification is sulfur content, and here the magic number is 0.5%. If your sulfur content is higher than 0.5%, you're referred to as a sour crude, and if your sulfur content is less than 0.5%, you are considered a sweet crude. Sweet crudes are considered preferable because there's less work at the refining stage to get the sulfur out, which makes it faster. Also, low sulfur content fuel is considered more desirable when traveling around environmental areas. So more than likely any of you work on board ship, you'll have 2 fuel oil tanks. One is your heavy fuel oil tank with high sulfur content, which gets you from point A to point B. And then you'll have a tank you transfer over to, your low sulfur fuel oil, which you'll have to use to transit ecozones. I like this graph because, one, you can see the place names, geographical regions. Also here on the left hand side it measures the sulfur content, measuring sweet and sour, and on the bottom it measures the API, the density, and less later over here and heavier here on the left. I'm going to start off with Venezuelan crude oil. Now this stuff is really thick and dense, very low economic value. It's used for making roads, asphalt, stuff like that. High sulfur content as well, not very valuable. Down here on the far end is the best, well, by criteria wise anyway, is West Texas Intermediate, and then Brent crude. Globally, you'll hear more about Brent crude because, one, it's exported all around the world. West Texas is only used in the United States. So Brent crude, anytime you hear a price for crude oil posted anywhere in the world, usually it is Brent crude. Another thing I'd like to make note of here, one, because I've transported it in the past, is Arabian Light. So for any of you who maybe transported oil out of the Persian Gulf, you might have carried an Arabian Light sweet crude or an Arabian Light sour crude. This one here is sour because of the sulfur content, but sometimes they refine it for a parcel or 3 and brings the sulfur content down here, which increases its value quite a lot. I know in the first couple of slides I said I wasn't going to read to you, but in this particular case it may be necessary. That graph I just showed you, I really like it. One, because it shows you where everything is to on the scale. The light and sweet crudes, Brent in West Texas and Bonnie, dialed down the bottom right hand corner. They have a high API gravity, low sulfur content, low viscosity, high flammability, and therefore are referred to as paraffinic oils. They're great because they produce high quality gasoline, which makes them very valuable, as you can imagine. On the other end of the spectrum, heavy sour oils, Venezuelan and Russian crude oils. They have a low API gravity, high sulfur content, high viscosity, low flammability, and therefore referred to as naphthenic oils. And the heavy crude oils are very low in value, and tend to be used as bitumen feedstock. These next 2 slides refer to 2 terms which I need you to know. The first is conventional oil, and the second is non-conventional oil. Conventional oil is probably what you naturally think of when you think of extracting oil from the ground. There is a reservoir under the surface. You have a drill rig on the surface. The drill rig drills down into the reservoir, and oil flows to the surface naturally through the natural pressure of the reservoir. Unconventional crude oils are a type of petroleum that is produced or obtained through techniques other than the traditional oil well extraction methods. Remember we talked about the oil window a couple of slides back, where anything organic compounds under correct pressure and temperature between 80 and 220 degrees will produce oil and gas. Also, we talked about the things that were not cooked properly would produce tar sands, shale, items of that nature. That's what you're kind of talking about when you're talking about unconventional crude oils. So instead of drilling for them, you're actually digging them out of the earth. You're going to have to add chemicals and water to extract the hydrocarbons out of the solid structure. Also, with the adding of the chemicals and the water, it is less environmentally friendly and it's also more expensive. And this is what we're talking about when we're talking about unconventional crude oils. Next topic is oil reserves. And if you see in the darker colors, Saudi Arabia, Mexico, Canada, maybe even a little bit of Venezuela, we have the most. But if we go back a slide, you'll also keep in mind that Venezuela up here and Mexico are very low-end type grades of crude oil. And out of those four countries, Saudi Arabia, Venezuela, Mexico, and Canada, who do you think supplies the U.S. with the most crude oil? Any takers? If you guessed Canada, you would be correct. You'd be surprised at how many people do not understand the term oil reserves. It could be for, like I said here in my readings, it could be for a well, it could be for a single reservoir, a field, or a nation. When I talk about oil reserves, I want to use an example of, let's say we have a reservoir and there is 100 barrels of oil in it. I'm just using 100 barrels as my example. Obviously there'd be a lot more than that before we go drilling. That 100 barrels is referred to as what oil in place. So that is all the oil in the reservoir itself. But that is not the oil reserves. The oil reserves are only the things you can extract from that reservoir. If you drill a hole into the reservoir and put a well in there, just on the natural pressure of the well pushing out the oil, you will only get anywhere from 5 to 10 of those barrels come to surface. All right, that is primary extraction. Also, there's secondary extraction methods where you will pump carbon dioxide or water or gas into the well to increase the pressure and therefore extract more oil. That might bring you up to another 30%, so you're probably at somewhere from 40 to 45% of extracting all the oil in place. And then there's also enhanced recovery methods. We'll get into that a little bit later on. I'm getting a little bit ahead of myself there, and probably bring it up to maybe a whole 50%. So out of the oil in place, let's say 100 barrels, which we originally talked about, you probably only get 50 of them out, and the 50 represents the oil reserves. On this slide is a few terms I want you to understand. The first is recovery factor, and the next is reserve growth. We already talked about oil in place and reserves. So let's use our reservoir, our oil in place, 100 barrels as our example. So our reserves that we can get out of that is 40 barrels. So that is a recovery factor. The ratio between the reserves and the oil in place, we can get out 40 barrels with just conventional, traditional, primary and secondary extraction methods. Now, when I talk about the reserve growth, your reservoir itself is not growing though. The 100 barrels, the oil in place is always going to stay the same. What's going to improve though is the technology that you use to get it out. So as technology and the science between it all improves, you actually get more oil out of your oil in place. All right. So therefore your reserves are actually increasing. Although the oil in place, the 100 barrels, is still remain the same, your recovery factor is improving and hence your reserves grow. Hence the term reserves growth. Now, I'm not an expert in this particular topic, the proven, probable, and possible reserves, and I don't want to read out a definition to you. So this is how I get my head around it to think about the concept, and hopefully you'll like it. It might not be totally technically correct, but like I said, it's how I get my head around it, and this is how I'm going to teach it to you, and hopefully you'll like it. So what I use is my reservoir, and I got 100 barrels in it. If I drill a well, and just through natural pressure of the well, 5 to 10% will come out. Okay, and that's what we talk about primary extraction. And that is almost a given. That 90% certainty I'll get so much come out, and that's what we're talking about by proved reserves. Just that method alone, drilling a well, natural pressure, pushing it out, I'm going to guarantee 90% certainty that I'll get that much. Okay? Probable reserves. Once the natural pressure of the well dwindles and production stops, then you move to your secondary methods. Secondary methods are injecting water or carbon dioxide or natural gas down the well to keep the pressure of the reservoir up, which will push out more oil. Okay, and the 50% certainty of that working and getting more reserves out, and we've already mentioned that the reserve quantity from that method is another 30 to 40%. So by that time, you're at 50% of your reserves coming out. And the last one is possible reserves. And I always use enhanced recovery methods, where your well now is at the last stages and you're trying to get as much out of it as you possibly can. And enhanced methods are things like injecting steam or chemicals, or actually burning the oil down there to make it less viscous and to come out. And the certainty of that happening is about 10%. And that's how I get my head around the term proved, probable, and possible reserves. This is just a continuation on from that last slide, but something I think you should know. There's these annotations of numbers, 1p, 2p, and 3p, and sometimes they're used instead of the terms proved and probable and possible. So 1p represents all the proved reserves, 2p represents the proved plus the probable, and 3p represents the proved plus the probable plus the possible. Okay, companies, when they have a new discovery in a reservoir, they have to declare their 2p, which is their proved plus their probable. There's a lot of p's in this particular lecture, isn't there? Also, interchangeably as well, instead of 1p, you may also see p90. The 90 represents the 90% probability that the oil can be brought to market. So gang, that's the end of section 1. If you could go into our textbook and read chapters 1 and 2 if you haven't done that already, it'd be greatly appreciated. It'll give you a better understanding, a little more detail as well than what I've given in just the slides. They're the Coles Notes version. And also there's a little mini quiz that has to be submitted by the end of the week. And if you can participate in the discussion topics, that'd be greatly appreciated. Thank you for your time. Let's start week 2.